So, yeah, so he has been here since Sunday. So he already ate so many things like sambal balado and things like that. So he already getting used to spicy food. Okay, and Professor Joseph Mollier is our guest professor, and he will stay here at Bandung until next week. So we had some kind of nice discussion with PhD students, and today he will deliver a talk about optimization technology and its application to support eco-friendly initiative. Okay, so probably I will read some of his CV. So let me open the document first. So Professor Mollier obtained his PhD in engineering physics from University of Bordeaux, French, in 2005. And since 2012, so he is a full professor of aerospace engineering at ISAE Aero, France. So his research interest is, well, actually quite a lot, but I think if I can say it with some words, it's about design optimization for aerospace, topology optimization, and then also how to use this kind of technology to support eco-friendly initiative. Okay, so thank you very much again, everyone, for coming. So I guess we can start. So Joseph, let me check everything. Can you share your screen again? In full screen, okay, good. Now if everyone should be able to hear me, so I'll give this to Joseph, please.
Okay, thank you. So thank you, Pram, for this introduction. Let me check. Yeah. So I will discuss about our research in engineering optimization technology, and I will show you our progress, and it's more specially dedicated to open source initiative, right? In order to product eco-friendly structure or aerospace system. So here is a list of my funder, partner in research. So you can see ANR is the French National Science Foundation. And then the foundation of my institute is also supporting me on this topic. And you can see École Polytechnique also. And I've got funding from both Airbus and Honor. So I'm coming from Toulouse to Bandung approximately in this kind of one day and several hours with a stop in Doha. So my visit here, so you can calculate your plane travel footprint with the stop in Doha, and it's about 2 ton equivalent CO2. In France, we target that every citizen reach soon 2 ton equivalent CO2 per year. Okay, so I will try to demonstrate in my next talk why it is important. So just some key figures about ISAE Aero. So this is probably the oldest university in aerospace. We have more than 120, so the 115 years old. Okay, we started in Paris in 1909. So that's why we've got so many alumni, right? We are more than 140 professors, and each on the campus there is approximately 2,000 students. 40% are foreign students, right? So, we've got a lot of academic agreements, so 100, and approximately 300 PhD students on the campus. And our campus is shared also with ONERA, which has a center in Toulouse. So a bit about the educational program. So what you can see is that we have different diploma. So I begin with the highest, so that's PhD program, you know this. We also have a postmaster. I mean, for people who are specialized, for example, in material science or mechanical, they can go with us, and in 1 year, they have a diploma dedicated to aerospace. And then we have a master level, okay, 2 years, sorry. And the specificity is that we don't have this research program inside, okay. Most of our students do internship in industry for 6 months. So this is for, in general, foreign students, okay. But we also have one dedicated to French and excellent foreign student. That's the ingénieur Isaïe Supero. And in fact, it's a diploma between who started undergraduate and you graduate at the end with master level. That's the idea. And we offer also, I will give you some detail about this, a spring semester in aeronautical engineering. So in the Ingénieur Supérieur program, we got approximately 200 French students in the first year. And then second year, we have 100 students coming from Spain, US, Dutchland, etc., etc. So we merge here. Most of the courses are in French in this program. So Toulouse is an aerospace city. So we are south, and the Airbus is north. And in between, we have downtown. And you can see all around the city, you have plenty of activities dedicated to aviation and space, right? Either academic, industrial, or in between. So research, R&T, Research and Technology Institute. So here is the academic program for the spring semester. It's in English. We got accommodation on the campus, and you can see a small photo where we have approximately 24 students coming from different countries: Sweden, Malaysia, Korea, United States. Plenty of, so maybe there is an opportunity for students of ITB of coming during this spring semester. We've got 5 courses: aircraft design, aerodynamics, propulsion applied, and structures, control, and then research project. So let me show, this kind of alumni we got. So we got the CEO of Airbus as an alumni, president of Bombardier, CEO of Arianespace. We got test pilot, astronaut, and most probably the well-known is Enrico Honda, the creator of the first jet aircraft. But we got also the founder of Dassault Aviation and Dassault System, okay? So Katia has been created, so the core by this guy, Francis Bernard, which is also an alumni. Yeah, you can find another list of alumni.
So everyone, there is technical problem, so please wait.
This one is not working.
So I'll send a message to.
The system crashed.
It's not a good time for working. It's so like the sounds like it's like
Although technically you can still continue, but we will see. Yeah. Yeah, yeah.
Ini ada yang ini udah dicampur.
Ini bisa jalan nggak? Zoomnya oke, nggak ada masalah. Buat ini, sebenarnya. Oke. Setiap orang join Zoom dulu. Zoomnya Zoom. Ini saya bakal taruh di situ. There was a short circuit.
Ya.
Well, how can I write that?
Barangkali nanti pakai seperti versi Zoom aja. Nanti
Oh, situ. Oke. Jadi supaya bisa melihat kita ini ya, kita masuk ke link Zoom. bit.ly kolam
Okay, I need to want my microphone or
your what? I'm sorry. My microphone probably yes. Okay.
yeah, okay.
Yeah. So I think it's okay if you see so that you can use your microphone.
Yeah. I need to put my
So do you want me to continue?
Yeah, in 1 minute. So this is a macro.
I think it's okay.
Yes. Ya, ya, kita semua orang masuk ke sudut sini. Jadi bisa
Oh no, I think he.
That's okay. Gimana Q? Apa sih suaranya Jason ngomong?
Is it okay here? Sound?
Alat-alatnya pakai itu besar, tapi tidak ruangan.
Ruangan di mana? Tapi
Kalau ini ada lagi, pakai zoom aja.
Oke, kita lihat meeting dulu kalau gitu. Oke. Ya, ya.
Ini ada dulu.
Ya, lebih baik. Oke, Oke. Ya, ya. Saya meeting break. Saya harus kasih tahu. Ya, ya. Pak, kenapa ada apa? Ya, oke, slide kelihatan.
Your dribble.
Kameranya udah masuk, kamera udah masuk.
Oh, you can
Cek
use
suara,
the
cek suara.
speaker. Yeah. Is it okay?
I think it's okay. Oh, it's
Mungkin kita ini
Yes,
Logi.
Yeah. Okay. Okay.
speaker.
Yes. Can I setting your audio?
Yeah, but the speaker.
For setting up volume. Maybe for setting up. Yeah. Okay.
I
Okay.
think it's okay. Okay, so
sorry for that.
no problem.
But I think I need to open the screen. Share screen.
Yeah, I can share the screen. In Zoom.
Yeah. Can you try to move the slide?
Yeah.
Yes. Okay.
Is it okay? Yeah.
Yeah, it's okay. So we need to be very sorry because there were some technical problems, but I hope everything is fine now, so we can start. So Joseph, please.
Okay. So let me continue presenting this Despero. So it's maybe not clear here, but the CEO of Airbus. And especially in our topic, we got Giuseppe Cataldo, who is a specialist at and then we get this bunch of astronauts, is an astronaut coming from France, Italia. Both of the nationality are represented. And they are passing through Toulouse and Superior sometimes. So a little bit about me. So as Frank said, I'm professor instructor in multidisciplinary optimization, and I worked a lot with Airbus. So on the left, you can see the topology optimization design we made of the Python. Okay. And on the right, you can see the kind of topology optimization we can make for Wingbox. And what is interesting in this kind of design is that you don't have any pixel, right? It's an explicit vision of topology optimization. But of course, it relies on density field. So you can see on the top view of the Spero. And for myself, I came from Bordeaux, which is near the Atlantic Ocean. And we have a pretty strong university there. And so it's above 2 hours and 200 kilometers far from Toulouse. So in fact, I did the same trip than this kind of fuselage part, okay? Because they were constructed near Bordeaux and they took the Garonne, the river, in order to be assembled in Toulouse. Okay. So I did the same trip than this kind of aircraft parts. So blah, blah, blah. This is my research experience. Anyway, I will skip to my team research. So with Airbus, I'm doing a lot of MDO for aeroelastic wing design. And then with Onera, we are doing mostly aircraft design using surrogate models, using Bayesian optimization. And that's why I call it AI for E. This is for engineering, okay? And with the Delft, I'm doing a lot of digital fabrication. So the idea is to accelerate the design cycle from CAD to the printed part. And globally, on top of that, I'm trying to do what I call eco-optimization. It means better and greener, aerospace system. So taking into account environmental constraint in the design loop. And here is part of my team. So we can probably see some of my PhD students and some of my colleagues when they are and superior. And this was the last MDO PhD day we organized in Toulouse. So today we'll discuss about how to design better, okay? And for this, you have to understand that we can make a breakdown of each part of the life phase of a structure of an aerospace system. And so you can see here the different phases, so material extraction, manufacturing, transportation, use phase, okay, which is in this case the biggest one. And then you have at the end what you do with the system or the product. So you can reuse it, you can recycle, and that's disposal. And we can approximate the energy that required to do all of this life with the CO2 emission. Well, I will show you something. So of course, for an aircraft, 98 or 99% of the CO2 or the energy, it's in the use phase, okay? And for this, you need to understand the embodied energy and the CO2 emission. Both are a sum, and both are divided by the mass of material produced.
Maybe you want to make it small.
This one?
Yes, perfect.
Oh. So that's two criteria we'll use. And one important fact is that recently, I mean 2 years ago, the collective mass of all the material is above the mass of every living biomass, right? So it means we started to change something. And this mass, called the anthropogenic mass, double every 20 years. And if you think about Airbus' proposal that material will be the key for the next generation of aircraft, I think there is a mismatch. Because if you want to have a new float of aircraft in 10 or 20 years, you will have a massive and huge demand in material production, extraction, and energy. So for the summer school. But anyway, the facts are here. If you design something, you will need material, you will need energy in a massive way. So that's why several years ago, Cambridge University started to work on materials and the environment, product and the environment. And for us at Supero, we work on aerospace system, aviation, and environment. Of course, this can be the impact of the aviation on the climate, but it can be also the climate impact from the aviation. Okay. It means when it's hotter, for example, you may have more gusts, the amplitude should be more higher, etc., etc. Anyway, that's in French, but that's one of our pioneer. He was our he was working for the Ministry of Energy in France, and that's the dean of the scientific for nuclear energy. He has this nice courses online. Okay, so different products, different impacts. And I'll show you that technology will, in fact, evaluate this, do changes into this impact. So let's just compare civil aircraft and family car. You can see that the definition of impact are quite the same, right? Anyway, before electrification and after, you can see that there is a massive change, okay? Especially for decarbonized countries such as France with a lot of nuclear energy. I mean, this graph is so the right post-electrification is for country like France. For example, in Dutchland, just near France, the energy is carbonized. Okay? So you have a lot of electrical Mercedes, electrical BMW that, in fact, are running, but they should be running with the French energy, right? And the question is, what is the future for aircraft, right? And I'll show you some technology, how to optimize this, and that's the scope of the talk. So here it's CO2 equivalent or energy equivalent, but of course you have non-CO2 effects such as contrails that enhance the heat in the Earth. And of course, future sustainable aviation will have a more equilibrated impact. So that's in French. Thanks to hydrogen, sustainable aviation fuel, and electric or hybrid propulsion. And from the side of structure and materials, you can see for the car, for example, the material part, due to battery design, etc., is more important than in use in our country. So yeah, we really have to work on that, and that's my team is working on all these topics. So 3D printing, advanced structure for hydrogen, predictive maintenance, worst case design, and the ultra high aspect ratio wave. Okay, so if you're interested in environmental impact of the aerospace manufacturing sector, we've made this short courses online. So it's 10-minute max, but it's in English. You will have all the information related to how in Europe the aerospace manufacturing sector is working. Of course, we did not have data from Airbus. We passed from the other side, so from the supplier from Airbus. So it's a sort of inverse environmental impact. So a small question for you. So maybe it's not easy to read, but from this data, there is two aerospace material, two famous. Can you guess who? So that's not common properties such as Young modulus, etc., which will be too easy.
When you're asking
The kind of material, the name of the material. So in aeronautics, you have titanium, you have aluminum, you have a carbon fiber, CFRP. Yeah. So one of the major difference is metallic material are heavily recyclable. Okay. And composite is not. So you got one on the left which is not recyclable, and the other you can continue. For example, for metals material, I think that more than 50% of the production is reused. Okay? So that's really interesting from this point of view. So let's talk this after this introduction, and I will discuss about three things. So engineering optimization, eco-friendly structure, and I will show you the novelties of SMT or surrogate modeling tools. Right. And next Tuesday, I will have a talk for the summer school, more dedicated on sustainable aviation. Thank you. Okay, so let's start. So optimization is everywhere, especially in your cell phone. Does anyone in the room knows how it works, this kind of Shazam software for music recognition?
I don't know, but I mean, it's Sada.
Okay. So I'll try to explain. So for this, you need to understand what is time frequency map. So that's the evolution of the local frequency content of the audio you're listening, or your code versus time. Okay, so I mean, if you have a nice songs, you will have different frequency at different time. Okay, so that's one of the ingredient for Shazam. In fact, it's working with this kind of spectrogram, but we have a first step that is to simplify the spectrogram. So it's detecting the local maxima, right? So that's the blue square. And then we have this for so a sort of encoding of each song in a library. So I think the library here is different from my French Shazam. Anyway, at the first step, you record, okay, you obtain a spectrogram and you will try to match this. Okay. And after a few steps, you have a match. So it means you have something that is the nearest song in terms of time frequency content with one song in the library. Okay. So you need to match something, that's important. So match induces minimization. You need to define a metric, you need to minimize something, and you need to define stopping criteria. Okay, so sort of tolerance to run the algorithm. And at the end, if you have all of this, I think you can optimize. So if you want a really good start, you can have access to the online group of my colleagues from the US, Kim Martins from Michigan, and Andrew Lim from BYU University. Anyway, in aircraft design, you can have the coupling between all the disciplines. That's for me really interesting. So for example, at FTMD, you have people working on material, people working on structure, on fluid dynamics, etc., etc. So here, this is a matrix of elemental coupling between disciplines. And so at the end, you have fluid control, physics, applied mathematics, structural materials. And for me, structural materials, I will exchange information with all the other disciplines. And here is, for example, how I describe the structural materials in terms of topology, material choice, process choice, okay, for the design optimization. So the goal is to start for mass minimization to CO2 footprint minimization, right? And if I put this into the Breguet equation, we are on the right, okay? So we're working on this quantity. By the way, Breguet was a French aircraft engineer. By sharing through solvers, okay, but for a surrogate function, okay, that will have a quick answer, but of course you will have to construct the surrogate before, okay. So you will have to do some design exploration, like we did with Pram, and surrogate construction. So for me, you can see surrogate as the old school, new way of old school abacus, okay, that I've got during my lessons, but maybe the youngest researcher here do not know abacus, but not the software, the printed version. Anyway, SMT for me is a way to accelerate the design. So it's a common work with a lot of universities. You can see Michigan University, UCSD, Polytechnique Montréal. It was the story began also with NASA, and Onera is the main, Onera and Superior are the main supplier. And of course, soon with Prime, you will have novelty, so ITB will be there. So a recent example I've made was A design. So AIS mean high altitude, long endurance UAV. So you can think on the left here. So in this case, we have no propulsion, okay? It's for example. So here we have no fuel burn, okay? So what is important is to improve the CO2 impact of the system. And for this, we've got 4 disciplines, so aerodynamics, structures, energy, and environmental decisions that, in fact, are proportional to the mass, okay? Here you can see that the avoided carbon is dependent on the mass here. And then you multiply by a carbon factor. But of course, these AIL have solar panel, and that's how they produce energy. So thanks to all my co-authors here. So it was a nature paper, really difficult, but we managed. And the goal at the end was to select the best material for skin and spa and the layout of the solar panels. What is important in order to understand the MDO, when you have a slight increase in the total weight of the drone, it leads to an increase to the weight of the battery and also to the solar panel avionics in order to propel an heavier drone. But you also have this kind of effect called snowball effect. So when you have an increase in the weight, that induces a more important lift from the aerodynamic point of view. We have to have the equilibrium lifting our weight, and thus it increases in the overall weight of the drone. So that is something called snowball effect. But at the end, what you can say is that the optimal drone geometry is a ultra high aspect ratio wing. Okay, so let me pass to the second example of MDO application. Again, that's on an eco-friendly initiative, and here we have decided to work with the whole life cycle. Okay, so we have data from a database called EcoInvent, and we'll discuss construct the life cycle assessment and discuss this with MDO. That's not easy. So LCA is normalized. Okay, you have a bunch of software to do this. We use the open source software. I will discuss about it. So to define a proper goal and scope definition, to do the inventory analysis, I will explain it to you. Select the impact and difference between midpoint and endpoint impact. So that's it. So a small example, I've got two process, P1 and P2. In red, you will have minus scalar, for example. So it means you need something, and plus you produce something. Okay. So here is the production in electricity that used two processes, P2 here, that you can express in mathematical term like this, and P1, so input-output relationship for transformation, that you can express in mathematical term like this. So in fact, for P2, you need X2 liter of fuel to produce Y2 kilowatt hour of electricity. And of course, you produce impact, so CO2 and SO2. Okay. The same for P1. And when you plug the two in order to really produce the energy, you have to match this 200 liters. And then it's quite easy. In fact, it's solve a linear system. So I will need 100 liters of crude oil. I will produce 40 kilograms of SO2 and 120 kilograms of CO2. Okay. So that's the basis of life cycle impact. Okay. The next part is impact assessment. And it is, here I will show you a comparison between eco-design and MDAO approach. So MDAO, we use open source software. LCA, we're using independent industrial software. You have to pay. So many simulation, low amount of variable. And then there is a huge numerical framework for LCA because you have a large external database. Okay, that can be open source from states, or you have to pay like EcoInvent, and this is the larger one. And on the left, you have engineering teams like me and you, and on the right, you have dedicated team that are often do consultancies. So our Python tool try to merge the two solutions. It's called LCA for MDO. So we use these two papers. So one for Brightway, which is the open source solution, and one for OpenAMDO, which is also open source. So our first try with my co-authors here was in fact in space. Okay, so we had an MDO framework which aims at optimize the glow with some kind of design variable that are the stage, the trajectory, the mass here and here. And of course, we have a strong constraint that delta V final is superior or equal to 0. So that preliminary design, but at the end we got a X star, so a full design, and we got also the global warming potential in terms of CO2 equivalents. But here we have no coupling because we just made the LCA of X star for optimal design. Okay. So it's just the sort of post-processing. And by the way, you can see that for micro launcher, the manufacturing part takes almost 20%, okay, with respect to the aviation. And the goal of the work is really to work together, LCA and MDO. Okay, so we transform this on the left into the right problem, okay, where we integrated a small environmental module for every technical discipline. Okay, and this idea really helped to solve the problem LCA and MDO together. So what we've done is to call an optimizer called PyMove. So in fact, it's using NSGA2. And for example, I will show you this example where we want to maximize the range, so minimize minus range, and minimize the global warming potential, the two in the same. So of course, here you have two objectives. So the Pareto font will appear in the next slide. I hope so. Oh no, there is some. So here are the 4 disciplines. It's a variable, and the difficulty was to convert the MDO variable into LCA database entries. And this is the mapping we've made with some strong assumption, because, for example, for motor, and we're using an hybrid King Air, okay, so an aircraft, and we use data for the automotive world, so especially for battery and yeah. So if we did that with these design variables, yeah, so if we take the trajectory also into account, but in this case, we pick the most classical trajectory, so the mission does not have much more effect. Anyway, we obtain this kind of graph where you have the global warming here and the range of the electric aircraft. Okay. So the functional unit is a kilometer flow, and the LCA scope include manufacturing and flying over 1,000 cycles at max range with fuel and electricity. So at the end, you will have this kind of approach of each dot in the each dot color is the hybridization during cruise. Okay. So you have these points, 50% of cruise, these points fully electric cruise. So you can, as a designer, use this kind of graph in order to do the selection of how you want to fly, okay, between electric and fuel. That's really important for the kind of designer we. And for example, here are the optimal value for the nautic miles range, okay? And you can see when you change the range, all the design variables are changing a lot. Okay? That's a strong coupling between all the disciplines. And of course, for the design variable, when you reduce the range, it decreases the hybridization, it reduces the engine size, and it increases battery weight. So for this, you need the code we've made, you need to pay EcoInvent, that's the database, and you need to use right-of-way and FTMD as the software dependencies. So let me turn from aerospace to structure, okay, and some eco-friendly structures. And for this, we start with the life cycle, for example, for vehicle. And the question is how to find the structural design, material, and additive manufacturing process with the lowest life cycle CO2 footprints. So the main question for me, restricted to metallic materials. So that's the left part. I think I will have time to introduce you to some composite material results. So here are the advantages on the left for additive manufacturing. And of course, there is cons also. Anyway, if you want to do CO2 emission, and at the first hypothesis, if the material choice is given, it means you just have to do mass minimization, okay? And of course, the other things is energy demand for production or water stress, etc. I will show you at the end. So we need to find the best structural arrangement, and for this you use topology optimization. But we, so I think I will skip this one. But anyway, at the end, we will use this kind of multi-scale topology optimization. Okay. So it means you have very tiny unit cells that are adapted locally to the force pathway. Okay, that's it perfectly matched, and it helps to reduce again the total mass. So it's ultra light structures. So that's unit cell design, and for me, it's how to incorporate the digital materials as a new design variable optimization problem. So you need to know to design a unit cell. So using this paper, this is a nice review from DTU and Delft. You need a topology optimization framework. And you need, so on the left, you have the standard results at a certain resolution, and on the right, you get the multi-scale approach. And you can see the elements are already thinner, okay? But you have more connection in between. So it means we may have created some kind of composite fiber directly for thin structures. And each small element is a unit cell. And of course, you need a good PhD in order to do this. So here is my PhD. So blah, 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 there is a different solution in the literature, but we work on a solution that is well-oriented for unit cell and well-connected. That's our main difference. So we divided the problem into multi-scale into a two-step approach. So we have the macro scale problem, and we have the micro scale, where so macro scale will try to design the full topology, and micro scale will try to find the best unit cell per zone. Okay. So for this, we need to define interaction between the two, and that's three variables that are three unit cell properties, so the macro density, angular, and cubicity. And then we want to minimize a certain scalar value. I don't want to enter into detail, but here are the density plots, the orientation of the cell, and the ratio between the principal axes. And at the end, we obtain this kind of structure. So normally I came with a structure in order just to see. Anyway, that the top 88, so the open source software versus ours. And if you do something like this two-step approach, it could be long. Okay, so we decided to accelerate the design by learning this phase, unit cell design. So we sample, we use SMT, and we use this database to construct the surrogate model. And so right now the code is really fast. I don't want you to enter, but yeah, from the three unit cell variable, we construct tensor database and the optimal microstructures. So that's 3 inputs, 6 outputs. And if you do this and you choose the nearest optimal solution, because the Gaussian process is a regression, and here we use finite difference skis with this step, okay, and you find an equivalent solution. Here is the way it works through iteration. So in blue you have the objective function. In orange you have the sum of your strengths. So at the end, in this case, that's minimization compliance. So it means you have the high stiffness. So we do not take into account stress in this case. Do you see any difference between the left and the right? So blue and black and blue. Yeah, you've got something. Small, yeah, so small things like this. So as you know, this kind of structure are really thin, really so the one of the dimension is largely superior to the two others. So it's a kind of thin beam element, and it's subject to buckling. Okay, so in order to avoid local buckling, we rigidify here. So you're right, you found it, just like my students. Here, probably there. No, there, over there. That's that. Yeah, yeah. The other, yeah, the other side. So that's the main difference. Of course, we analyze the solution with abacus in linear, nonlinear, etc. And we were really happy to make the test at the end with metallic structures. Okay, if the material choice is free, it is more complicated. Okay. Probably I will skip some slides. Anyway, yeah, Edward worked on this topic. It was a huge work, and we published into several papers. So the link between eco-design and topology optimization. So just to introduce you, we've got standard case from HB development, Cambridge, for this kind of structure, beam, plate, etc. And we add a new dimension. Okay, it's to select the best topology inside test cases. Okay. And here, what is interesting is that we've made the theoretical development for establish the relationship between compliance and volume fraction. Okay, so if you take HB beam, you have three variables, you have some fixed, and you have a constraint, which is a deflection in the middle, both for the two testings. We also have this kind of free variable, fixed variable, and constraint. Okay, we will really mimic this. But at the end, we want to minimize CO2. Okay, that is depending on material selection. And for metallic, with a strong assumption that from it's for you, the Poisson coefficient is not changing a lot. Okay. D is the domain, okay, design, and T the thickness, right? So it's a constraint program through the deflection, and the material is given only by Young modulus, density, and CO2 impact. Okay, only these three variables. And of course, the volume is between 0 and 1. And if you want to have the total CO2 impact, you have the carbon intensity multiplied by the mass. The mass is given by solution of the topology optimization problem, so the volume fraction. And then you add the CO2 in use of the vehicle, which is also dependent on the mass, but also of the life duration. So for an aircraft, life duration, so a typical aircraft, over a 30-year lifetime, flying 3,500 hours a year as an average, at an average speed, blah, 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 it will lead to this value, number of miles. So if you're familiar with topology optimization, there is this nice thing that at very low fraction, the structure is just like truss-like structures. Okay. And that's one fundamental well-known results. Okay. But we developed some mathematics, and I have no time for publishing it, but it's online. And at the end, yeah, you can see the effect on volume fraction on the density. So if you aim at a very low fraction, you need a very adapted materials in order to support the loads. Okay, so that's why we target ultra-large structure with material and process choice. So blah blah blah. What is important is on top. Yeah. So yeah. So we'll start from the quadratic form, the compliance. So here are the two versions, and then you can rewrite this. You can rewrite the mass function of the volume fraction, and we can establish this relationship between the compliance and the F multiplied by the deflection. So all is hidden between by inversing the K matrix for solving. Blah blah blah. If we made a HB theory, and if it's T of free variable, so that we have a full expression of mass function of VF and F of VF, which is the compliance for a certain volume fraction. And then you recognize the material here and the geometry here. Yeah. So it's some kind decoupling or the effect, and that's how works HB diagram. Okay. You have a decoupling of material, functional, and topology elements. So it's really close from HB theory. If you do this, you need to minimize something. This is this quantity. Okay. And in our case, it's often bounded solution. Okay, but here for illustration, we have to minimize something. If we took this information for long distance aircraft, which is the FRC, we can compute blah, 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 the final results using the Pareto front for different materials. And this solution, so here we have aluminum, stainless steel, titanium, and nickel, and we will find the best index. Okay, so that's F3. So if you do this, of course, for the same structure, same load for a bridge, which is staying on the ground, and in the aircraft, you will have not the same material selection. You have approximately the same mass, you have the CO2 emission, and in this case, it's a total, so with the whole life cycle. And of course, the results is dependent on the application. Okay. If you want to see a more advanced problem, you can have a look to this paper. Okay. Yeah, so here I will switch from metallic to composite structures. And I think, yeah, here we will work on the eco-fiber resin, so the couple selection. So it means here I'm not selectioning the best material, but the best couple between fibers and resin. And there is a really nice bio-resin that are now in the aerospace structures. Okay, so this work has been a pioneer work. That's the work of Martins and Tim Brooks. And in fact, if you want to see the wing box, it is in Michigan. In the aerospace department, you have the, I think it's 20 meter long wing box in the composite with what is called the two-steer fibers. And they work for NASA for this topic. And it was, of course, decision of this kind of path for the composite. So, of course, when you lower the wing mass, you lower the fuel burn. Okay. So either you can put more people inside or you can have a max range. And of course, at the end of the MTO, this is a ultra high aspect ratio wing. Okay, we decided to work on this kind of application. So that's a bracket, and that's the amazing result of Schmidt 2020. Yeah, where you can see really the fibers that are created by topology optimization, right? So in order to do this, you need to change a bit the compliance problem, and you introduce a new variable here, which is a local orientation of the fiber. Okay, and then it's quite the same. So we did it for 2D structures. You have the open source code, which is here. It is working only with Python. Okay, so this is a case, and you can see the local orientation and density checked with the 3D model. Inspired by this really nice work, we wanted to do the numerical design of this. So that's a work of University of Manchester and Tudor, I think. And here we wanted to find the best material to minimize the impact, find the best printing direction, and of course, check the printability. So the problem in 3D is more advanced. So you have two local orientation. That's the density. Anyway, blah, blah, blah. The compliance is a joint one. And we use a different kind of couple of fiber resin. And we also check for aluminum as a reference results. Anyway, I'll show you. So if you have access to the ANSYS solver, yeah, you can play this. Okay, I'll show you. So this is a density optimization. So the variable density with respect to several load case. And you can see we have this penalization factor with respect to iteration. So we are more penalizing the density through iteration. So sometimes it helps to obtain results. And this is a normalized constraint. And here it's the fiber orientation. So red is X, green is white. Yeah, through iteration. Blah, 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 I will not enter into detail, but you can have compliance versus CO2, and we can have a Pareto front of selection of fiber and resin. The resin are here, it's really small. You can see bamboo, and I think it's carbon and aluminum as a reference point. So we can do a slice of each results, and we can also check the printability of the structures. And of course, we do not reach 100%, but anyway, that's depending on initial orientation. And I'll show you another, to conclude this part, another concept, that's the full wing box concept. So it has been established by NASA during the MadCat project, okay, where they use unit cell assembled together. And this has been extended to a realistic case by Karen Woodbox, and it has been fabricated by NASA. So you can see the drone wing box here, really ultra light. Okay. You have full of void and some structural parts. So we did it for this CRM case, which is open source, with 3 load cases with the aluminum material. So it's not easy, but we have 3 load cases, so 3 answers. And we did the optimization for aluminum, and we have a gain of 27% compared to the previous results. Anyway, we extend this optimization program and put material as a parameter. Okay. So there is aluminum, titanium, steel, and a kind of equivalent CFLP. Because all of this is truss design, okay, truss only. So at the end, we would like to see who is the best. So we launched the 5 analysis, and we obtain the 4 analysis, and we obtain this kind of graph. You can see the deflection, you can see mass. So, sorry, it's a mean mass problem, and you have to respect volume fraction, stress, local buckling, blah, blah, blah. There is, I think it's the most advanced one. And what you can see is that CFRP has the lowest mass, but at the end, aluminum is 4 times the mass. It's quite the same deflection. Let's see. This one is the largest, the smallest. And at the end, we select aluminum because it has a total CO2 impact a bit higher, but it's really cheaper in terms of cost. So that's a proof of concept of greener aerostructure with lattice wing box. Okay, that's not published right now. I'll show you one of our last work. And what if you have other environmental constraints? Okay, so not only CO2, but water consumption, energy consumption, etc. For this, we're working at fixed topology. Okay. We extend the work of University of Wisconsin. And at the beginning, you have a fixed structure, fixed load case. And you have to decide about the section of each element, the cross section, and the material. And the material uses HB database. Okay. So in order to use the same kind of type of variable, continued, we use this encoder-decoder approach in order to project the database into a latent space. Okay. What we add is more design variables. So water consumption, objective function, so water, generation of waste, carbon footprint, energy consumption. I think this is all. So the idea is use variational autoencoder for continuous mapping, and you can see the inputs. So we have 7 inputs, which is Young modulus, density, yield, stress, blah blah blah, and we encode and then decode using mean and variance in the latent space. Of course, we have to use the well-known regularization here, regularization, in order to produce a good VAE. And this is what I call what we call a differentiable material representation. On the left, you can have on the latent space, so Z0, Z1, the CO2, and the cost. Okay? And you can have a kind of continuous representation of every material. So then we can minimize any quantity, okay, subject to the equilibrium, subject to stress constraints, bounds for the section, and bounds for the latent space. So the initial work was on the left. So we wanted to find the optimal areas and the best material at fixed topology. So we extend, so this is the compliance. This is all the constraint. And so that you can either minimize compliance or mass, and for example, minimize cost, CO2, energy resource, or water energy through the database information. What we add also is new information from the database. The first time you only have Young modulus and density, for example. And here we extend to cost per unit mass, yield strength, CO2 produced per unit mass, energy, and water required per unit mass. So if you do this and you try to solve a multi-objective problem, just like the other case we use PyMove, you can have this nice kind of graph, or you can see graphically the evolution of the section, okay? And the points represent the material chosen. So for example, here it's the mass versus cost graph. Yeah, we can do for compliance versus mass, which is really more interesting. And you can see there is a sort of discontinuity here between the best section. So you can see here the sections are bigger, but you use CFRP. And here some kind of section are smaller, but you use plain carbon. So if you want to have more detail, we have this last 3D case where we have defined what is called the equivalent environmental impact here. So that you can produce CO2 versus water versus energy, and available material. And so the best for us was this one that minimized the environmental weighted approach. So that's yeah, one point to decide. But again, the topology is fixed. So my next step is to mix topology and this, topology optimization and this. Okay, so I'm near the end, and I will show you what is SMT and what are the novelties. Okay. So SMT is a surrogate modeling toolbox. It means you have costly code, or you have experiments, or you have numerical model. You can work with both. And you want to avoid calling a new experiment or calling a new simulation that is costly. So X are your inputs, Y is that you want to predict. Okay? And so the data are used to learn this relationship. So more to come with Pram soon. Okay, so probably what you know is neural network, such as MLP or polynomial regression. Gaussian process is a bit more complex, but it happens to have more information, and the exact information is hidden here in green. That's the variance of the estimation. So we use it for optimization at fixed subjects. So that's Bayesian optimization. So let's say you have, so at the beginning, Safran called me and said, "Oh, Joseph, I want my computer are free this weekend. I've got 40 hours of computation, right? Free for you. Can you find the optimized solution?" I say, why not? It was a long time ago, but their design loop took almost 3 hours. Okay. So it means I've got a few iterations in order to reach the optimum. Okay. It was challenging. So often what we did is we produced, for example, a set of initial design of experiments. So let's say 30 hours. So I'll get 10 times 3. And then I've got 6 more experiments. Okay. So I've got 6 iterations to find the optimum. That's called, in fact, Bayesian optimization. You learn and then you exploit the function. Okay, so my simulation is expensive. I have my initial design of experiments. In practice, the size of X, the design variable, is approximately 100. And we want to compute Y function of X. Okay? And here is a cut X1, X2. And then if you're doing some MDO, you can replace any discipline by this kind of abacus. So the work started a long time ago, and now it's the version 2.4, something like this. So you can have access to the code, to the documentation, and here I'll show you what is error-based exploration. So it means I want the best surrogate. This is my only goal, to have the best surrogate. So in order to do this, I need to minimize the variance. Okay? And the GP is outputting a mean plus a variance at a certain point. For the GP, you must select the kernel. You have to find the optimal data. And that's, again, optimization into the optimization. So the first case is I want the most precise surrogate. And the second, I want to find a global optimization. So for this, we're using what is called expected improvements. That's Scala or criteria that is using both mean and variance of the estimator of the Gaussian process. And you can see here we're searching to maximize this quantity EI. And at each maximization, I will ask a new simulation. It's updating the surrogates and updating the objective function. And then I'm passing to maximize this one, and here is my new one. And again, maximize here, and I arrive to the global optimum. Okay. So I think I managed to resume in one slide Gaussian process and without math. That's interesting. So what we propose in SMT is to construct the best surrogate, okay, or to do unconstrained optimization. So the first question is, are your data expensive? Okay. And the next question is, if they are not expensive, they are cheap. So you can have an initial design of experiment that is large. If it is expensive data, if your data are not really smooth, you can do what we call mixture of experts. It means to automate the clusterization of the surrogates. So, for example, I can use in my design space several zones with data inside. And for example, this one could be least square, this can be a pregame, this can be a MLP, and blah, blah, blah. Okay. And we merge all these local surrogate into a larger one. So if you want to have a simple explanation, but you can use a quadratic model. You will have the coefficient of the quadratic model that explains the output function of the input, or an interaction between input. Okay, but of course it requires some engineering sense. Okay? And Pram and his students are working on this kind automation of explainability. We have this option if you put MOE is equal to 1, and you have all this data. Okay. And if you do this, it will compute MLP, NS, pregame, whatever, and it will select automatically the best function of your data. Okay. That's really cool for the engineer. So for the unconstrained case, okay, we call it efficient global optimization. So the question is, do you have access to the gradient or not? So not, it's derivative free. And if you have gradient, is it an estimation, the finite difference? Is it the direct, adjoint, or complex step, or automatic differentiation? All is possible. The next question is, do you have a large input space, engineering input space, so let's say 100? If you have this, I would be happy that you use KPLS. So that's a kernel we developed that is used to minimize this size. Okay. This minimization, okay, we are using KPLS when data is big. The number of hyperparameters are big. If not, you can use standard exponential or Mattern kernel. If you have a gradient, you can use gradient enhanced rigging. Okay. And finally, my advice is to use the initial DOE of 4 times D, the dimension of your input space. Okay. So if I have 10 input space, you will have 40 points to poke. Okay. So what are the kind of variable types available in SMT? And we work a lot on this topic with Paul Sav, our PhD. And at the beginning, first version, we only have continuous. And then we had all of this, okay? Discrete, categorical. So discrete, I can order it. Categorical, I cannot, okay? For example, the beam section, I can have the I beam, I can have the S beam, etc. I cannot order this because it's dependent of other variable and quadratic moment of inertia. And I can have a mixed approach. And hierarchical is a new one that, for example, if you are using a complex system design, you can probably lead to new variable with respect to iteration and optimization criteria. So we call it hierarchical. Anyway, if you want to start with the tutorials, they are online. Yeah. You can launch it directly on Google Kolam. Okay. It's practice. And I will show you two one in yellow. So the first one is airfoil, transonic airfoil analysis, where we have Reynolds number, angle of attack, and we developed 2001 simulation. That's the ground truss and the predictor pressure distribution. It will be soon online, and for this we use POD plus kriging as interpolation of coefficient. So right now it's not online, but soon it will be online. Thanks to Giovanni. And then thanks to Paul, we have this kind of Kaggle results. So it was a crystal system property for electrical battery, and we wanted to predict the crystal system class function of this kind of X. Oh, sorry. So X is on top, Y is the crystal system, and you can see some of the variables are integer, some of them are continuous. And yeah, what we have is the kind of classification with scikit-learn using 80% of the data to learn and 20 to predict. And you can see prediction are not so good. And here are the results with the opposite, with only 10% for learning and 90 for predicting. So it means with few data, by using our mixed variable, we are able to predict the crystal perfectly. So next question, if you have a constraint optimization problem, you can test online. You need to register, but you can test online. Okay? But you have no access to the code. If you want to develop academic contact, you have to contact me and Natalie, and I hope we will do an agreement in order to use a constraint optimizer, which is called Sigmo MOE. Yeah. And I arrived to my conclusions. So here is the kind of graph we can have in aviation, so that the mass versus the global warming potential production and manufacturing. So you can see from A300 to A380, this is a linear relation. Okay? So we need to change that. Let's keep into as a key information to take away that manufacturing is only 1% of the CO2 impacts. But anyway, I'll show you for the space application, it's different. Okay? For an electric vehicle, it would be different. And with Pram, we have worked on distributed electric propulsion, and we are transforming this into new technology. So think different in order not to have a pure line. And for this, you have to take into account so the Sustainable Development Goals of the United Nations. And I'm really happy that education, which is my work, okay, like you, is really important inside these goals. Educate is really important. So I'll show you a bunch of results for going to greener system, aerospace system and aerostructure. I'll show you how to use SMT, and definitely take a look. Normally it works on Kolam. There is the tutorial working well. And what we did recently with TU Delft was this link for education and research through PhD, and we launched Poland, sometimes in France, and I think it worked well. And our idea, together with the faculty, is to do the same here, so construct together a project and a research project and an educational project. And that's really important for me. Here are the information for open source tools, the paper of SMT. And by the way, we're working a lot with REA on the topic of optimization of neural architecture, neural network architecture through SMT. And if you want to connect, ask me on LinkedIn. Here is my email. I've made some popularization of my work on LinkedIn. And I think, yeah, this is the last slide. You can see on Mars, there is a small logo of Isao Cipeo. So we're really happy of this because our colleagues from the physics departments did one instrument inside this project, and yeah, it's the first one on Mars, so we are happy.
We have quite time for question and answer session, for discussions. So if someone might have questions, so
I think I have several questions, but I think I'll just say one of them first and then see if others have questions. Okay, so my first question is just it's a bit annoying, but in the second part of your presentation, in the eco-friendly structures, we showed several results or many results of topology optimization structures. But I think, as far as I can observe, everything was based on the density based. Are there examples that use the level set?
Yes, you can. For example, for us, it's better to use density. And the answer is that I started topology optimization with this. Okay, so that it works well. We have we can progress. We can involve new development very easily. But anyway, with Giovanni's work, we're also working with implicit neural representation, and here the geometry is a level set, a sign distance function. So it means we're starting a sort of evolution in order to pass through level set.
Okay, because my concern is on the verification of the adjoint, of course.
Yeah.
For the level set function, well, I find it difficult to compare with the objective with the final difference, let's say. But for density based, it's always relatively simpler, right? Because the objective will be continuous in the with respect to the design variable. However, for the level set, it is discontinuous.
I think there is you should probably read Aller's book. Grégoire Aller.
Yeah. Oh, yes. I think I've read it, but I'll see it again. If I remember correctly, they verified their solver using analytical solutions.
Yeah. Anyway, I have no clue for you right now.
yeah.
Okay, that's it.
Okay, thanks. Maybe any other questions for the audience? Yeah, Prof, please.
Thank you very much for a very interesting talk. So, to my understanding, this is a right? But of course, in the future, we hope that we could really make this.
Yeah.
So, I wonder your opinion about how we could add manufacturability aspect to your model here.
Yeah, so for example, in composite, we have this criteria that is compatibility. And of course, what we need to do is to be close from people that manufacture. So that's why we are working in close collaboration with Tudor, okay, because there is one scientist there, Kunal Masania, that is currently having a great lab in 3D printing. So you can 3D print almost everything. Just like the MIT course, build almost everything. Okay? Yeah, and this is not my case. I can build almost nothing by myself. So I need to conduct collaboration. But anyway, often I say that when you produce this, So Pareto font is different solution. That's the end of my job. Okay. And the guy should take the STL, work on the design, select what he wants for the material. Maybe if it's far away from my choice, it's up to me. I have not closed the loop because this is not the scope of, we are more on design optimization. So I have a solution for an engineer in a fast way. And what is great is to have a set of solutions like Pareto.
Or in the end, probably you'll have something like the trade-off.
Printability is a numerical measurement. It's not linked with the machine directly. So, there is several work on find the best structure without support, for example. Minimize the number of support. And for this, you need to have the process in mind because it's machine dependent. Just sit.
Well, there depends on something because I was reading a paper from NASA. So they consider the penetration the process. And that's what you mean.
Yeah. But what is great with the American guy is the guy do not hesitate to construct the ring. Okay, and this is not my case. I don't have this money to do that. Sorry. Yeah. But the goal was to construct this, and they construct a UAV, they construct a race car using ultralight structure. Me in my lab, if I want to do that, I need to fill 100 forms, find 1 million, build maybe a building for doing that. So it's too difficult for me.
Because Americans just can't do anything.
Yeah, at the beginning, in the 60s, if they wanted to go to the moon, they go. You get money.
Right. So, any other question, or probably from Zoom?
Over there.
Jesse?
Yeah, just maybe follow-up question because it's the same question I asked from student. Usually when we see a presentation, this optimization that seems like we are complicating the simple stuff. Yes, I haven't seen any example about how to optimize a complex system because why do we need to complicate simple systems like Cadillac or something? Why don't we try to solve a complex system like the rib or the joint?
Yeah.
Or maybe like that. I cannot see it. If so, in my perspective right now, I still like Prof say it's we need to connect it with how can it be connected.
Yeah.
And that's the part of design because we need to take into account many factors.
I heard this point often, and it's not that easy. Researcher that can do design, optimization, and fabricate complex structures. For this, for me, it's even a big project. Okay, so if you want to build a micro launcher or a CubeSat, you're not alone, right? And for me, I think I just help the other to have a set of solutions. But of course, you can try to use dedicated software such as OptiStruct or Adobe Fusion. They help the designer with in order to construct complex structures. But this is not our case. We are not developing software. We are developing open source software to help the designer. But anyway, yeah, that's a good point for you.
Maybe the software can have some adjustment of the user.
Yeah.
Make it less unnatural, or make it more manufactured.
Yeah.
So what do you think? If we have a very efficient aircraft, a complex aircraft with its wing, with its tail, and so on, and it's already designed like that, but if we put it in your software and we set up the maybe dynamic parameters or aerodynamic efficient, will it output another aircraft that is more efficient than this aircraft?
So yeah, so that's a good question. Often the people come from industry to say, "Oh, I want to optimize this, blah blah blah." But at the end, an aircraft is probably optimized by engineers from 100 years. Okay, so it means already from the beginning, the structure were optimized. Propulsion were optimized by engineers, and it's difficult to have a large improvement. Okay. Often, if we have 0.5% in aerodynamic efficiency, it's great. If we lose 5% of mass, it's great. So that the design variable domain optimized. So what we develop is also for new project. And here, if you have no idea, for example, topology optimization can give you a shape. Okay? Yesterday, this guy was showing how to do this. Sorry, I'm sorry for the first name. I don't want to. Anka. Yeah. And that topology optimization can help to find a new design with unknown. You know the paper from the guy. Yeah. So he found an aircraft from nothing. Yeah.
Definitely we will able to do that.
Yeah. So you need new project, new idea, you know, and then we can help to have something really new. If not, yeah, if not, what is the most similar between Airbus aircraft and Boeing aircraft? It's the kind of same technology.
Yeah, well, coming from flight dynamics guy, I think I want to have a software that in which I can put with not just the forces and moment, but maybe the dynamic parameter like the ratio, frequency, number of frequency.
Yeah.
But the thing when you deal, you do that, right?
Yeah, deal with, yeah. I've got so in my other presentation, I've got so sorry, wait a minute. So so there is a bunch of open source software, and I've done a curated list. Where is it? Yeah. Yeah, so a good example is the Martin's group, MDO Lab. where you can have everything to make an aircraft. Okay, you have structural software, you have optimization software, you have fluid software, you have geometry. Okay, in order to produce the what you want as geometry, either a car or an aircraft. You have a simple aircraft design tool here. You have multidisciplinary optimization tool, all is open source, and you have SMT. What is great with open source software is that you not only have the code, but full documentation and example and tutorial. And I just list some tools available online for decarbonizing air transportation and for aircraft design, and the list is not ended. So yeah, that's the idea, is to, for example, I just forgot there is a nice tool at Imperial College in your field from Palacios. There is I can't remember the name, SharpEye, which is a tool for designing a flexible aircraft, taking into account dynamic of flight, etc. And it's fully in Python. It's you can easily plug it into optimization, and we use it for several projects. So what is interesting with open source is that you can reuse it easily. But of course, if you have someone that is in your field, you gave him, in fact, your computer. But anyway, it's in a sense better for collaboration, better for discussing if the people have tested the software and you can see the limitation, etc.
Okay, I think we have time for one more question. Okay, so
Thank you. Thank you very much, Joseph, for the very interesting presentation. So actually, I just want to say, well, as you said that actually, well, during design there are so many things. Sometimes the production process and other things that actually relate what you have already mentioned in your latest part of the presentation about the non-numerical. So in the design process, sometimes we have options, IB, but it will also combinatory. So we have of that. So I just want to know whether, since it is an approximation, so I just wondering whether to make, if there is a very combinatorial problem, it very how useful, how beneficial using this?
Yeah, if you have combinatorial approach, there is no secret. So what the main technique is branch and bound. That's only limits the combinatory. For us, we can mix discrete, etc. So that we map the design field with points, and that's really sparse. Okay. But in fact, we do not limit the combinatorial. Okay? We just have something that give information in a discrete domain. That's a sort of transformation of discrete into continuous. Yeah. And you know, in machine learning, people are doing encoding. Okay? So encoding, hot encoding, one-hot encoding is the way that you transform discrete variable into continuous in order to solve the problem with continuous. But I don't think there is a magic solution. Except probably give a priori solution to limit the combinatory space. That's the only, to give some information about that.
Maybe just what's already asked. It took a real product, so there are so many options, let's say.
Yeah.
So maybe that's why one of the things very difficult to see. Optimize everything and then optimize everything.
Yeah. Yeah, I don't think it's not my business.
Yeah.
But in order to do that, for example, in Europe, there is a collaborative project so that, for example, with Onera, we provide only the optimizer, and then people are doing the logistic and blah, blah, blah. But that big project, 100 person, millions of hours of computation and a lot of meetings in order to solve the optimization problem of designing aircraft, fabricating them in every country, blah, 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 assembling them. For me, it's too complicated for me. I don't feel I can do it alone. Yeah.
Like you mentioned, starting from scratch with nothing and then having some solution is just already.
Yeah. For me, that's a really strong point of optimization. To give a new idea, that's for me very important.
Okay, okay, so I want to thank you again, Joseph. Thank you. Long day for you from Tulus to Jakarta, and we are very happy to host you here. So we still have 14 days to go. So yeah, have a nice weekend. You can enjoy it. So like Palapi suggested in the summer, I think we'll get it.
Okay.
Anyway, I want to say thank you to everyone
Thank you
for attending this session. So I think this is, well, we have been collaborating and we are hoping that there will be more collaboration between IIB and Supero in terms of both education and research. Well, in fact, on Tuesday, we visited French MC and hopefully they can support us with hopefully with many things. And finally, Joseph felt the heat of Jakarta. It's totally different city from pollution and stuff like that. He said that Bandung is, well, more peaceful. Yeah. So thanks everyone in both
Thank you.
And both of you thank Mr. So let's applaud the board. Thank you. So I'll close this session. Maybe we can take a photo. Zoom-nya dari situ. And also thank you to Pak Firman who